All right. In this video, we're going to talk about continuity of a function at a point, and then in class, we'll extend that to continuity of a function over an interval. So why don't you pause, copy this down, then press play. All right. We say that a function f is continuous at a point x equals a, or at a given x value, if the graph of f has no holes, no breaks, no vertical asymptotes at x equals a. You might remember a teacher telling you that you're continuous at x equals a if you can sketch the graph at, on, and after x equals a without lifting up your pencil. Okay. All right. More formally, what it actually means and how we verify it is through this checklist. So f is continuous at x equals a if three things occur, and all three things have to occur. F of a is defined. So we're not dividing by zero. It's not a negative under a square root. Okay, f of a is defined. Number two, the limit as x approaches a of f of x exists and is finite. Okay, so it can't go to infinity or negative infinity. That'd be a vertical asymptote. And remember, what the limit existing means is that the left-hand limit is in agreement with the right-hand limit. Okay, and then the third thing is, assuming the first two are true, what that limit is equal to has to be what the function equals at that spot. So the limit tells you what's coming in from the left and from the right, and if we have to agree with what the function says at x equals a. If those three things happen, your function is continuous at that x value a, right? All right, let's check out a couple examples. All right, so again, I would ask you to maybe pause, copy out this panel, and then press play. All right, so in example one, we've got a piecewise defined function, and it splits, the two pieces stop and start at x equals 4. So it's a natural question to ask, are we continuous at x equals 4? And I'm going to go through the checklist and see whether or not we are. If we fail any of the checklist steps, we're done. We're not continuous. If we pass all three steps, we are continuous at x equals 4. Okay, so step one. F of 4 has to exist. So let's calculate f of 4. I'm plugging in x equals 4, so I'll be using the top piece of my piecewise defined function. That would be a 4 squared minus 15. So I get 16 minus 15, which equals 1. Okay, so yes, I can calculate f of 4. I get a coherent output. All right, number two, does the limit exist? So because this is a piecewise defined function, it's very important I do a left-hand limit and a right-hand limit, okay? So limit as x approaches 4 from the left, I'm thinking 3.9s, 3.99s, all things that would utilize the top portion of the piecewise defined function. So I'm going to replace f with x squared minus 15. If direct substitution works, great, I'm done. So let's try direct subbing. I get 4 squared minus 15, which we just did. I got 1. Okay, so the left-hand limit exists. How about the right-hand limit? So 4 from the right, I'm thinking 4.1s, 4.01s. So I'm thinking x value is greater than 4. So I'll be using the bottom part of the piecewise defined function. So f for these guys is 2x minus 7. And again, if direct substitution works, great, I'm done. So let's try direct sub. I'm going to plug in x equals 4, 2 times 4 minus 7. I get 8 minus 7, which is also 1. Okay. All right. So note the left-hand limit equal the right-hand limit. They're both 1. So we can conclude that the limit as x approaches a of f of x is equal to 1. So it exists. It is finite. So I've passed the first two steps, the first two items on the checklist for being continuous at x equals 4. All right. Third one. Does f of 4 equal, question mark, the limit as x approaches 4 of f of x? Well, f of 4 was 1. The limit was 1. So yeah, it does. So in this case, our function f has satisfied all three of the requirements for continuity at x equals 1. So I can say f continuous at x equals 1. Okay. All right. Example 2, determine whether or not this rational function, one polynomial divided by another, is continuous at x equals 1. okay? So I'm going to proceed with the checklist again. So step one, let's make sure g of 1 exists. So I'm going to plug in x equals 1, 3 times 1 squared, 2 times 1 plus 1, all over 1 minus 1. So I see a problem. The denominator is having me divide by 0, all right? So that, I don't care what the numerator is. I can't divide by 0, does not exist, okay? So g of 1 does not exist. I have not even gotten past the first item on my checklist, so I can automatically say g is not continuous at x equals 1, right? We know from our earlier work at x equals 1, we're either going to have a vertical asymptote or we're going to have a hole in the graph. And I think since the numerator is not equal to 0, I think we can have a vertical asymptote at x equals 1, which is beyond the scope of this question, but yeah. Okay, so one thing to note about the definition of being continuous at x equals a is if we have a function that's continuous at x equals a, direct substitution is the answer to how you calculate the limit, right? Because the third step of being continuous at x equals a tells you that the limit as x approaches a of the function is equal to f of a. That's direct substitution, okay? All right, one last panel. All right, so I press pause, copy this out. One thing that you might have thought about in the previous two panels is that checking continuity is a tedious process, and that's for checking it at one single x value. Eventually, we're going to want to be able to say, hey, this function is continuous for all x's or all x's on this interval. So it'd be nice if we could increase or streamline the process for checking continuity. And these rules are going to start that process. So if we know that f and g are each continuous at x equals a, same a value, then we get a whole host of other functions that we know are also continuous at x equals a. So for example, f plus g of x is going to be continuous at x equals a. F minus g of x is going to be continuous at x equals a. F times g of x is going to be continuous at x equals a. F divided by g is going to be continuous as long as g of a is non-zero. So as long as it's not causing us to divide by 0, all right? And then f of x raised to any positive power, like the 1/2 power for square root or the 7th power. That's also going to be continuous at x equals a. And finally, a constant, a number like 7 times f of x, that new function will also be continuous at x equals a, all right? So given little simple building blocks f and g, I can build more and more complicated functions, and for free, I get that they are also continuous at x equals a. All right, so that sort of explains why we can immediately say that polynomial functions are continuous at all x values. Like a polynomial function is 3x squared plus 7x plus 1. You know, it's the function x squared. So as long as I know x is continuous at 1, I know x squared is continuous at 1. And x is just a line of slope 1. It has no holes or breaks or asymptotes anywhere. All right, so we know it's continuous everywhere. So the rule would tell me, well, x squared is continuous everywhere. Rule 6 would tell me that 3x squared is continuous everywhere. 7x is continuous everywhere. Rule number 1 would tell me I can add 3x squared and 7x, and that's continuous everywhere. All right, so I can use these very basic rules and build up more and more interesting functions and know that they're continuous. So for example, we know that all polynomials are continuous at all x values. And since I can divide and still preserve continuity as long as the denominator is non-zero, if I take one polynomial p of x and divide it by another polynomial q of x, as long as q of x is not 0 at the particular x value, this new p of x over q of x, rational function, is also continuous at that x value, all right? So pretty much polynomials are always continuous and rational functions are always continuous except where their denominators are 0, okay? All right, this also tells us that for polynomials and rational functions, direct substitution is going to be a great way to calculate limits. It'll always work for polynomials, and it will almost always work for rational functions as long as what I'm taking the limit at does not make my denominator 0, okay? All right, Okay,